Hello everyone, my name is Sidhant. This is going to be a lecture about string hashing. It's in one of the topics on the intermediate division, Div 2. Yeah, let's start off. A brief intro about myself. I've been doing competitive programming since like 5-6 years, and I represented in IOI. Right now I'm a final year college student in NUS, and yeah, I've been to the ICPC World Finals itself also. Cool. Is this lag issue with other people also? If yes, then do let me know. I'll try to figure out. Okay, so we have the slides here. So let's do share screen. Okay, so I hope everyone can see my screen. I'll just give me a moment. Yep, so okay, so we have this, right? Everyone can see the string hashing slide, right, with the scribble. Cool. You can find the recording, I think, on YouTube later on, or even on Unacademy. As for the lecture slides, these slides are there on the Discord channel, in the string hashing channel. I uploaded them like an hour back. We'll be referring to these slides only for this lecture. Yeah, I think we can start off. Okay, so firstly, giving due credits, I took some of the concepts from CPU algorithms websites. You can just Google this up. It's a pretty famous website. And some of the things are taken from Codeforce's blogs, like a collection of Codeforce's blog. So what's the agenda? First, we'll understand why one should know about string hashing, like why is it so good. I personally like string hashing a lot as a concept, like it's very powerful, I feel. What is it? How do we do it? Its analysis, that's kind of like, it has some probabilistic arguments in it, or like which are tricky to get. So we'll go through that. Applications, pitfalls. Applications is basically problem solving aspect. Like how do you solve problems using string hashing. So what's the motivation? String hashing lets you, most often than not, optimize a brute force approach to a string related question. So let's say you have a question where your brute force of order n square or order n cube TLEs. Okay. If you know how to do string hashing well enough, then there is a very high chance, like for some of the problems at least, that you'll be able to make your slow solution slightly faster by a factor of n or something and get it to work. But like the typical way to think about string hashing question is still through the brute force method, that okay, I'll just compare strings or something and then it will work out. So at a very high level, think of it that it speeds up comparison of any two strings. So conventionally, if you compare two strings, one of length n, the other of length m, then the complexity it takes to do the comparison of two strings is order n plus m. Let's say you have this string s1, this string s2, and you have to compare which one is smaller, which one is bigger, or you have to compare are they equal or not. The time it will take is at most order n plus m, in worst case, if the elements are like almost equal at all positions. String hashing generally makes this order 1 or order log n. Our implementation will primarily be considered with order 1. So like for any two strings, are they equal or not, we are able to tell that in order 1 using string hashing, which is not the case for traditional brute force methods. So if you have an algorithm in which you do a lot of such comparisons and your complexity is blowing up because of doing all these comparisons, then you can just use string hashing at some point. We'll have examples, so it's more clear. Now, why do I think it's a very powerful data structure? Well, if you just look at string data structures, there are a lot of data structures. There's Nath Morris Pratt KMP algorithm, there is suffix array, there is suffix trees, there's palindromic trees, there is Ahokoda C, and probably others also. Like I know Z algorithm is there. Then I think there are some other data structures also, or algorithms. There are a lot of algorithms. But as a general rule of thumb, for a lot of problems, there, like I won't generalize this to say that it's true for every problem, but for a lot of problems, one of the alternate solutions to those problems is through string hashing. So as an intermediate, or as even like anyone, I would say, like a lot of people including me don't have expertise in all these data structures. Like I don't understand KMP that well to be able to tackle a very hard question of KMP, but most often than not, a question that's doable by KMP is also doable by string hashing. So that's the benefit that you get. Then string hashing is very versatile in terms of string data structures. Even if you don't know a lot of string data structures well enough, but you know string hashing very well, you can crack a decent number of questions just through string hashing. That's how the benefit is. So why doesn't everyone use it? It is slightly tedious to implement. You can get some details wrong, like picking which modulo, picking which primes. Should I do the modular arithmetic on the go or whatever? So your implementation needs to be clean for both the things, not to give wrong answer because there is some probabilistic argument which we'll explain later, and also not to give TLE because it is sometimes like slow or something. So yeah, like the implementation is the part where sometimes people fumble a bit with string hashing. So what is it? The goal is to have a fast method to map any string to an integer. So you have this function h. Let's say this is the set of strings, and you have a function h, and it makes that string an integer. So maybe there is a string dog here, and your function h made it integer 5. Maybe you have a string hello here, and your function h made it a string 7, and so on. So you match every string to using this hash function. A hash function is basically just a function which takes in the string and gives out the output as an integer and gives you an integer. Now what properties you want is these 4 properties. What's the first one? If the two strings are not equal, then their hash shouldn't be equal. So basically, if I have to compare dog and hello, that are they the same string or not? Instead of comparing dog and hello, because that will be slow, because I'll do it character by character, I hash them and compare the integer 5 with integer 7. Since 5 is not equal to 7, I should be able to say that dog is not equal to hello in terms of strings. Okay, mathematically you can say this. H of s, if both the strings in the input are not equal, then their output should also not be equal. And if you're hashing dog or hashing hello, let's say, and it goes to 7, it should always go to 7 during your runtime of the code. No matter you do it at the first execution, like first line of your code or the 10th line of the code, it should be the same hash value. It shouldn't be like you are picking, like it's hashing to different values every time you run this within a single run. Obviously it's possible that you compile it at different times and it gives you different values because you have some random seed in your code. That's possible. But within a single run, within your piece of code, if you're hashing dog 10 times or hashing hello 10 times, then all those 10 occurrences, the hash value should be the same. Given s, we should be able to compute h of s fast. Basically that we should be able to hash fast, right? And your hash should look like an integer or a long or a pair of integers or a pair of long. Basically something O1 in size. That's the idea. It should be small in size. The hash value after hashing should be small in size. Cool. So first poll question, do you think this is possible, what we just described right now? Do you think there exists a string hashing method or a function h which can provide us with all that power mentioned in the previous slide? So I'll set up the poll. Do you think that this thing is actually possible? Cool, I think we got enough input. So, well, the answer is actually not. It's not possible, I would say. According to my definition. Can you show the slide again? Sorry. Yeah, the reason being, take this example. Let's consider all alphabet strings of length 100. and we convert them to single integers, right? How many unique strings can we have? 26 to the power 100, right? Because it's a 100 length string. Each letter, each dash can have characters from A to Z, so that's 26 possibilities. And you have 100 such dashes, so 26 ways into 26 ways into 26 ways dot 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 into 26 ways, which is equal to 26 to the power 100. So these many strings you can have of 100 length. How many different integers do we have? 2 to the power 32, because it's a 32, 4 bytes means 32 bits, and each bit you get two options, either put a 0 there or a 1 there, so you have 2 to the power 32, roughly 10 to the power 9 integers that you can store in an int, different integers, like you can store 1, 2, 3 up to 10 to the power 9. You can see this is bigger than this. It's obvious. It's like the quick calculation is 26 to the power 100 is greater than 10 to the power 100, and we know 10 to the power 100 is greater than 10 to the power 9, right? So we know that this holds. So how will we be able to ensure it? What's the issue now? Basically, I'm saying your string domain is very big, but your integer domain is very small, relatively, right? So there will be cases which you can't avoid, that string s1 mapped to this integer x and string s2 also mapped to this integer x under the hash function h. There will be cases like this, you cannot avoid them. This set had to be of the size 26 to the power 100 if you had to avoid this case. Basically, this function cannot be injective. Can't be injective. That is, there must be two elements in the domain, which is your strings, which map to the same value in the output, and that's bad. So this is a very strong assumption, I would say. You can't get all these properties true 100% of the times. So what you can get is the fixed definition of string hashing, which is this thing changed. Basically, you have this with high probability clause. It's very important to remember this clause. Can you explain again, Pranay? Okay. So what I said was that the number of strings you have is very large. As an example, I took all the 100 length strings. So that's the number of strings that you'll have is 26 to the power 100. But you're trying to convert each string to an integer, and the number of integers you can have is only up to 10 to the power 9, which is relatively very small. Think of it this way: if you have a domain of size 30, so you have 30 elements here, and you're trying to map each element to one element in this domain which is of size only 10, then there must be some element here to which multiple elements get mapped, right? That's what's happening. That under this hash function, there must be some elements here which map to the same thing, which is bad. We didn't want this. Notice, we wanted this, that if they are different, they should hash to different things. But that's not happening always. Sometimes they will map to same thing and you can't avoid it, because the size of the right side is smaller than the size of the left side. So we have this fixed definition, which is that we say if the strings are unequal, then their hash should be unequal with high probability. Exactly what Ritik said, that we have to minimize collisions that happen. This is known as a collision, when two things which are not the same map to the same thing and collide actually. Even if you use long Srivatsan, then also it won't help that much, because now your domain is 10 to the power 18, but still your thing was pretty big, 10 to the power 100. 10 to the power 100 is still bigger than 10 to the power 18. I mean, it will help somewhat, like it's not like it won't help anyways, but it will reduce collisions, but it won't eliminate them. You need this to be at least of size 26 to the power 100 to eliminate any collision, which you can't get. I didn't say it's, I did just said 26 to the power 100 is greater than 10 to the power 100, just to approximate, just to give you guys an idea of how big 26 to the power 100 is. It's definitely bigger than 10 to the power 100, right? If you can't suffice 10 to the power 100, how will you suffice 26 to the power 100? That's the idea. Someone asked in the questions, will we see the implementation also? Yes, I will cover the implementation. Okay, so yeah, so this is the modified variation, where you say that this should happen with high probability. So that means HS1 becomes equal to HS2 with low probability. I'll define rigorously what this probability is somewhat, but this thing should still happen with 100% probability, which is if they both are equal in the input domain, then they should be equal in the output domain. Yes, Hitesh said that does this relate to pigeonhole principle? Yeah, the proof is pigeonhole principle, that if the left side has more elements than the right side and you map each element of the left side to the right side, then two elements of the left side must map to the one element of the right side. How about big integers, Sidarshan? Sidarshan, you can think about big integers, but one issue that you'll get is if you use big integers, you won't get the benefit of O1. In normal integers, you can compare two integers in O1, right? It's pretty fast to compare two integers. If you're having big integers, the comparison is no longer O1. If the integers are, say, 2000 digits long, then the comparison actually ordered 2000. It's kind of like going back to the string version and not really hashing it. Hashing generally means restricting it to a smaller domain, which we are doing using our hash function. So how to do string hashing? Yeah, we are discussing the issue right now, that what are the issues with string hashing and what is its objective. Now we move on to the important thing, how to do this string hashing thing, right? How do we define this h function that we are talking about? So the most common technique which people use is polynomial rolling hashing technique. Yeah, so given a string s, what is pigeonhole principle? XD, you don't really need to know. If you understood the previous idea that left side is bigger than the right side, so two things must collide, then it's okay. You can read it up yourself, but it's not a requirement. Given a string, this S0, S1, Sn, so each of them is a character. I'm representing characters. Your h of s is this thing. It's a formula on the characters, right? Example, let's do an example. Let's say your string is dab. Okay. Now your h of this thing will be d into p. Okay, for simplicity, generally we will pick p to be 30 in this lecture. Okay, so d into 30 to the power 0 plus a into 30 to the power 1 plus b into 30 to the power 2 whole modulo some number. Generally we will pick it to be 10 to the power 9 plus 7, the classic comparative programming modulo. Okay, now notice I can't multiply letters, so just think of d in its integer representation. It's the third letter, so think 3 here. So 3 into 30 to the power 0 plus 1 into 30 to the power 1 plus 2 into 30 square modulo 10 to the power 9 plus 7. Okay, this is the hash value of dab. This will come out to be some integer, we don't care. What does p represent? P is basically some base. It's not really a prime. It need not be a prime. I just use the variable p here. It's not necessary to be a prime. Don't confuse it with primes. Oh yeah, sorry. D is the fourth letter. My bad. So criteria of picking p, we'll discuss that. For now, just think of it like it should generally be bigger than your alphabet size, which is 26. If you're using only the letters A to Z, then you're using 26 letters. But if you're, let's say, using alphabets from A to Z plus capital A to capital Z plus 0 to 9, let's say all these things are present in your string, then you can easily calculate. It should at least be 62, because 26 from here, 26 from here, 10 from here. So it should be more than 62. Add these up, 26 plus 26, 52 plus 10, 62. So it should be more than the alphabet size. That's an important thing to keep track of. And you do everything under this modulo. Why? Because you don't want the answer to overflow, right? You don't want it to overflow. Okay, I'll make this screen full screen. You don't want this thing to overflow, the mod. If the mod overflows, that's like, you want everything to still remain an integer. It's possible that the inner thing, this expression is bigger than modulo, or maybe like a lot bigger, very big. It's possible. So what we did here, just to give you guys an intuition, we made a polynomial in p. In our case, p was 30. Look at this expression. This is a polynomial in 30, right? It looks like x0 into 30 to the power 0 plus x1 into 30 to the power 1 plus x2 into 30 square. You could have more terms also if the string was longer, but it looks like a polynomial in 30. These are the coefficients, so maybe denote them by C0, C1, C2. So that's why it's known as polynomial, because it's a polynomial in terms of p. Okay. Why is p more than alphabet size? We will learn from peers also. Yeah, I was thinking that you can't see the questions actually happening, so I think it's better this way. Cool. So the hash is a polynomial in p. The hash depends on the length of the string. We denoted just now that the summation goes till the length of the string. Right? This is the same as Rabin Cup. Yeah, kind of. It's almost the same thing. We'll discuss the analysis, how to determine the chance of collision. The order of the characters matters. Notice, why does the order of characters matter? If you take dab, hash of dab, it will be it most likely will be different from hash of bad, because position of b and d changed. Here d was being multiplied with 30 to the power 0. Here d will be multiplied with 30 to the power 2. Here b was being multiplied by 30 to the power 2. Here b will be multiplied with 30 to the power 0. So it will change. This is just like writing the string in its character form. Like string is a sequence of characters, right? So this is just a character of that sequence. String. And is contained within 0 because of modular arithmetic. Okay. Any doubts up to this point? I'll explain what breaks when you do that. Yeah, you can use ASCII values if you want to, but then you'll just have to keep p probably bigger than 255 or something, because max ASCII value is 255. So you should hopefully keep p bigger than 255. We'll explain why 1 + 7 is a good mod. If it overflows, the issue is that you no longer have, like, it's no longer under the modulo world, which is bad. I mean, you can't, like, hash value shouldn't be negative or some arbitrary number. It should follow this formula. We'll be using this formula everywhere. Like, it should follow it. Another way to think about this is kind of this way that a lot of people do. If you have a string bad, just think of it as a number in base 30 or base 26. Let's treat base 26. What it means is that this is the first digit, this is the second digit, this is the third digit. Now the first digit is b, that means the first digit is actually 2, the second digit is actually 1, the third digit is actually 4. So this is number 214 in base 296, which when converted to base 10 is 2 into 26 squared plus 1 into 26 to the power 1 plus 4 into 26 to the power 0 in base 10, which is somewhat similar to our hash function, right? The order is reversed on the exponent, but the idea is still the same. That it's a base like you're trying to represent this string in base 10, from converting it from base 26 or base 30 to base 10, and because when you convert it, it will be very big in the base 10, so you modulo it. That's the idea. So now, why did we say rolling? We said rolling because if we know the hash of a certain s, then we can easily calculate the hash of s plus x, where x is a character, single character. This is easy to calculate. So if I give you h of s, I don't tell you what s is, I just give you h of s, and I give you x, and I ask you what is h of s plus x, then that's doable. Just look at the math formula. What's the formula for h of s plus x? Let's assume that the length of s is n. Then this formula is summation I goes from 0 to n minus 1. Just look at this formula. si into p to the I plus x into p to the n. Just think of it like a big string with x concatenated at the last position. So the last term will be x multiplied by something, right? So x plus p to the n whole mod. Does everyone understand why this expression holds? The one that I wrote just now. Why is h of s plus x this certain expression? This is just like, I just feed it in here. Now notice this thing can be broken down into I just rewrote it using modulo arithmetic. Just took this first term, modded it, added the second term, modded it, and modded it again. That's normal modulo arithmetic. Now you can rewrite it as h of s plus x times p to the n mod of this entire thing. Now this thing, basically, look at this expression. This expression is basically just h of s, what we were talking about earlier, right? So we got this formula that h of s plus x is equal to this thing. So given h of s, given x, and we know p also, which is like 30 or something, if we can calculate this thing fast, if we can calculate this thing in O1, then this entire thing can be calculated in O1, because we already know this. We already know h of s. So we just calculate x times p to the n fast, and then the entire thing is O1 calculatable, right? So given s and x, we were able to calculate, we were able to add one character. Think about it like this. This was the string s. Now it looks like this with the x, right? This is s plus x. So we were able to add a character to the right pretty fast in O1. Like we calculated the new hash value quickly. So that's why it's a rolling. You can keep on rolling towards the right or the left. You can think about it on your own, why you can add in the start also. Similar math expression will come out and you'll realize. Sarthak said a plus b percentage mod equal question mark. Where, Sarthak, I don't understand the exact part that you're asking, but okay, yeah, you have that property here. A plus b mod equals a mod plus b mod whole mod, which we are using. Yeah. Anyways, I'm assuming basic familiarity with modulo arithmetic in this lecture. So now think about a string s. Think about all the prefixes of that string. Let's take the string to be something like apple. What are the prefixes? Prefix 0 is just a, prefix 1 is ap, prefix 2 is app, prefix 3 is appl, and prefix 4 is the entire thing, appl. Right? So you have all these prefixes. If we know the hash of a given prefix, we can calculate the hash of the next prefix fast. Let's say we know hash of p2, and I tell you, you have to add L to it, because p2 is app. I say concatenate an L with it, add an L to it. Then you can quickly calculate h of p2 plus L, which is equal to h of appl, which is basically same as h of p3, the third prefix. So given a prefix, if you know this prefix hash value, just when you add one character in this prefix, you can easily know the hash value of this thing also, using this formula that we created, that this thing is basically this value, the green formula, right? So calculating the hash of every prefix is easy. It's order n. In order n, given a string of length n, you can just start from the first character and keep on applying this formula again and again. We'll go through the practical implementation, but that's the idea, that you can keep on doing this, right? So you have all the hash of prefixes. You know what's the hash of A, you know what's the hash of app, you know what's the hash of apple, complete thing. You know all these hashes. So now what you want to get generally for most of the questions is, how do I get a hash of a given substring of a string, right? So given a string S, I want to calculate the hash of, so this is the string S, there is this ith character here, jth character here. If I only think about this substring, what is the hash of this thing? Generally you want to calculate this. Can you give an example of concatenating in front? I'll give you an example. Let's say you have BCD hashed and you're trying to concatenate A with it. The idea is, what's the formula of formula of HABCD will be something like summation it'll look something like this. X, let's say you're adding X and this is S, hash of S. It'll look like X times P to the 0 plus summation I equal 1 to N SI times P to the I plus 1. Why plus 1? Because it's starting from the first character onwards. This entire thing under modulo. This is how this thing's hash will look. Hash of X plus S will look like this expression. When you try to open up this expression, you'll get X plus P times summation I equals 0 to N minus 1 SI times P to the I mod. Again, notice what's the magic here. This expression is basically H of S. The yellow expression is basically H of S. So just replace it with H of S and you're done. So this becomes X plus P times H of S whole under the modulo. Right, I just took P common because there was a plus 1 here. So I took that P common and then you get the same H of X here. You replace it. Powers can become negative, it's alright. Like negative powers will be solvable. If the value is big, yeah, that's what we explained in collision, right? That collisions can happen. So don't care about the adding on the prefix stuff thing. It rarely happens and you'll understand it once we go through more stuff. Just understand how this is more important, I would say. How do you add things at the back? Adding things at the front is just a math formula only, similar to the previous one. What if we use float values? You technically won't be able to widen your range because a float internally in the memory is represented again with 32 bytes only, right? So a float just takes 2 to the power 32 different values, or maybe it takes 64 bits. Then in that 32 bits, sorry, in that case it takes 2 to the power 64 different values. It can't take more than 2 to the power 64 different values if it's being stored in 64 bits. The issue is with the preciseness of the float. The float is not precise enough. It can only have these many distinct values. So that also doesn't help us if you try to think about it through that way. So you will have collisions. It's kind of like an impossibility result that collisions cannot be saved if you're trying to go for something O1. You will have collisions. It's just that you have to be smart about the collisions and try to minimize them in general. So okay, so given a string, how do we calculate the hash of a substring? That's the question, right? So the formula comes out to be this. So you're only concerned about the substring, right? So let's say your string was apple, but you're only concerned about this substring. What will be the hash of this substring? It will be P into 30 to the power 0 plus P into 30 to the power 1 plus L into 30 square, right? That's how the hash function is defined. Under modulo, just ignore the modulo. I sometimes forget to write it. Assume there is always a modulo. Now this thing is basically this thing which I wrote right now. Notice the exponent. I'm looping over all the elements from I to j. I hope everyone is familiar with summation signs. This is the lower bound of the summation sign. You're going from I to j, and you're putting in sk, the value, and you're multiplying it with 30 to the power position starting with respect to I. That's you. Do people understand why this is k minus I and not k? If it was k, then this thing would have been 1, 2, 3, which is wrong, which is not the hash value. The hash value, we defined it to start from 0. Like the exponent should start from 0 and go up. That's how we defined it in our original, this definition. This I goes from 0. Right? So it should go this way. Now now how do you write this hash value using the prefix hashes that you've created? That's the question. How do you, like, manually creating this sum is slow. If you create this, if you run through the sum, that's order n, because I can be very small, j can be very big, and going through the sum is slow. So how do you do it fast? You get this formula. I'll derive this formula right now only. It's pretty straightforward. It's doable. So think about what this formula is. What I'll try to show you guys is this thing is equal to this thing. So I'll just expand out this thing. What is h of pj? H of pj is the prefix up till the jth element, right? You had your string, there was a I, there was a j, the prefix up till the jth element, the hash of that thing is pj, h of pj. So what will h of pj expand to? Summation I equals 0 to j minus 1, something of that sort. Si, okay, let's use k variable k actually everywhere. Summation k equals 0 to j minus 1 sk times p to the I, p to the k, right, whole under modulo, minus what is hpi minus 1, summation k equals 0 to I minus 1. This actually goes till j, I minus 1 sk p to the k whole under modulo, and then we are dividing it by p to the I. This is our formula, right? How do we simplify it? Notice p to the k is coming common. So what you do is you break it into two sums. One sum is from k equal I to j minus 1 of sk times p to the k from here, plus another sum is from k equals 0 to I minus 1. I just broke it into two sums, sk to the power pk minus this thing sk to the power pk. Okay, this is also contributing. Basically this is the prefix sum for k, this is the prefix sum for I. I'm just saying that this portion gets subtracted away, so only this portion remains, right? So this portion looks like this. This term will become 0. This term will become 0, right? And whole divided by p to the I. Now how will this expression look like? This term got cancelled completely, it became 0. So you are left with summation k equal I to j minus 1 sk to the power pk whole upon p to the I. And since this p to the I is in the denominator, you can just bring it up in the numerator with a minus I, and you have the formula. Same thing that we wrote here. This is actually going till j. I made this typo. This is going till j. So you can derive it. So you know what's the takeaway of this entire calculation? That you know the statement holds true, which I just wrote. So this thing is equal to this thing that we want. That's the main formula that's useful in like the entire hashing thing, to know that this thing is there. which can also be written as this, but it's just the same thing. I just wrote minus I in exponent in the numerator. Okay, and we'll later show that calculating this thing is O1. If you know values of H, P, I for all I, if you know all these values, then you can calculate this thing in O1, because you can just do the subtraction, take the division, do the modulo in order 1. So how do you do this, all these things in order 1? That's the implementation part. So these 2 slides are basically the implementation. I've shared the code on the Discord link, the hashing.cpp. It's basically this code only. So let's assume that the string is of length at most 26. Let's say our mod is 1e9 plus 7. Let's say our base is 33 or 30. Anyways, some helper functions that people generally code for this question, for hashing, which are very helpful and avoid typos, is these helper functions. I would recommend to write this add mult function instead of manually writing mods everywhere. What the add function does is it takes 2 arguments, a and b, and basically gives back a plus b under the mod. So your result is a plus b whole mod. If the result is negative, then you add a mod to it and then you return the result. Why can the result be negative? Because a can be less than 0 or b can be less than 0. It is possible. It is possible that the numbers in the input are negative. Okay, another interesting question. Let's say you have a to be minus 10, b to be 3, and your mod is 5. And you do minus 10 plus 3 mod 5 on your C++ code. What answer do you expect? Do you expect the answer minus 2 or do you expect plus 2? This is option A, this is option B. Let's do a poll on this. I just hope everyone yeah. Do you get minus 2 as your answer or plus 2 as your answer? If minus 2 then A, if plus 2 then B. Okay, in C++ compilers you will get minus 2. In Java also you will get minus 2. Not sure about Python. I think it's minus 2, but not sure. I think Python has both methods. Like there is a method to get plus 2 also. So what I basically mean is that you can't assume modular arithmetic to work the same way it does in mathematics to work in programming. There is a slight difference, which is that negative numbers when moduloed, they stay negative, although they're correctly moduloed. Like after this it becomes minus 7. So the modulo did happen. It's not like the modulo did not happen. It's just that the number remained negative. So the number remained between the range minus mod to 0. But for a fact, if your number line looks like this, this is 0, this is mod, this is minus mod. If your original input number a plus b is here, then it will come here. If your original number a plus b is somewhere here, then it will come here. That's the idea. So if it's in this portion, then you have to manually add a plus mod to it to make it positive. That's what I'm doing here in this code. That if it's negative after the mod, then manually add a plus mod. Does the base depend on the character range? Yes. The alphabet size, like base has to be greater than the alphabet size. That's what I explained earlier. Now similarly, you have multiplication function. You do multiplication of a and b. You put the mod. If okay, this should actually be 0. It's a typo. Sorry, I'll fix the code later on. Yeah, it's a typo. If the result is less than 0, then result plus equal mod. Again, negative numbers can be multiplied. Good question. What is the purpose of 1ll here? Anyone in the chat knows the answer? So notice your a could be as big as 10 to the power 8, maybe, right? Your b could also be big as 10 to the power 8 or something like 10 to the power 9. And your mod in our example is 10 to the power 9 plus 7. So notice what will happen when you multiply these two big numbers. A will be into b 10 to the power 16, but this is bigger than integer. Integer can only store roughly up to 2 into 10 to the power 9. So it will overflow and it will become some negative value, which you don't care about. How do you fix this? You know modulo is around 10 to the power 9 plus 7. So modulo into modulo is within long capacity, right? Up like it's less than 10 to the power 18, 4 times 10 to the power 18, which is long capacity. So what you can do is take a, multiply it with 1 LL, which basically says 1 LL basically means 1 in long representation. So when you multiply this integer with this long, this gets typecasted to a long. So now you have a variable but in long typecasted value. Then you multiply it with b, which is an integer. But again, when a long and integer are multiplied, the result a into b is put in a long, not in an integer. Then this thing is not overflowing. Now you can mod it. After you mod it, this thing is now in integer domain, right? After modding it, it's small. And then you can assign it back to result, which can be an integer. So here notice it's a very tricky line. Like if you make a bug on this kind of a line, then your code will give wrong answer. This thing can be an int because we are doing this mod. If we drop this mod, let's say someone comes in and like removes this mod, then this code will also give still bug, because this is a long. Let's say the variable is 10 to the power 15, but you're trying to assign it to an integer, which is res, which will overflow. So it will be some negative value. So this precise statement is important. And even the order in which this 1 LL comes, if you put it somewhere to the left or to the right, you can observe that the typecasting doesn't work out correctly. It's generally preferred to put in the middle. I'm not sure actually, but yeah, you can try that out. This does work for sure. Yeah, for the reason I said. It's faster. Using integers is like twice faster than long. So some people put this hack in their code, like at top define hash define int long, which is alright, but it just makes your code slightly slower, like twice slower or something, roughly. I haven't explained actually that why is it greater than 26. I'll explain it later. Just assume for now that we have to put it above 26, but it still won't really write. It's a very tricky thing. I mean, sometimes you get TLEs in like hashing questions also or something, and then one of the reasons that's possible is because you're using long instead of integers. It's just preferred, like the most recommended ways to do it through integers. Obviously you can use long. Yes, it makes the code like roughly twice as slow. Okay. Now you have the power method, which basically says given a and b, calculate a to the power b under modulo. I'll put in some implementation of Java. I'm not sure the exact details, but like people do have these functions in Java also. I myself don't code that much in Java, so I'm not sure about the exact detail, but yeah, you can still do things in integers and everything. It will still work. Just like write this code in Java and it will work. So what power has to calculate is basically the exponent a to the power b under this modulo. Now let's do a show of hands of people who are familiar with. Actually, we'll just assume this. I can't explain this, otherwise I will waste too much time. Repeated squaring. So if you have to calculate a to the power b under modulo mod, you can do this in order log b. You can calculate this thing in log b. Binary exponentiation, correct. This is known as binary exponentiation, exponentiation, or repeated squaring. I'll try to find some blog on this, but like that's what this power function does. So mult function just multiplies. Mult function is basically given a and b, give back a into b under the modulo. This thing. So this is a into b under modulo, and this is a to the power b under modulo. I hope everyone, like, it's not immediate of why you want to do this, but I'll explain later. I hope like you can read up on some blogs on binary exponentiation or something if you're not familiar. Fast exponentiation is also another name, yeah. Fast expo. and understand this part of the code yourself. It's a completely different problem. I don't want to cover it. It will waste a lot of time. Just know that you can calculate this thing using this method fast in log B. Okay, cool. So now you have a pre-calc for your hashing. What you do is you calculate every power of base. So you calculate 30 to the power 0, 30 to the power 1, 30 to the power 2, up to 30 to the power n, all under the modulo. So this is under the mod, this is also under the mod, everything is under the mod, because otherwise they would have just overflowed. So you calculate all these things. So power 0 is 1 because 30 to the power 0 is 1. Then power 0 is basically the previous power. So basically what this expression says is 30 to the power I is equal to 30 to the power I minus 1 times 30. Right? Because power I minus 1 will give you just like the previous power. Just multiply the base again in it and take the mod of the entire thing. And you call the mult function just to do the modular arithmetic for you correctly. That's the idea of the mult and the add and the power function. To do the modulo arithmetic correctly for you, so that you don't need to care here how the modular arithmetic is happening. You can just wrap that around. So you don't have to put percentages everywhere in your code, which is one of the reasons why people have like let's say they missed one of the percentage signs at somewhere in their code, and now they can't, and the code is overflowing at that position because they didn't mod it and they can't figure it out. That's like a very common bug which happens, and this is like one of the ways that people avoid. Use these functions and do multiplications and additions only through these functions, so that we are guaranteed that we are basically in your this piece of code you shouldn't have the sign multiply or the sign plus. If you don't have them, then probably you're doing all the things using these functions and everything is happening correctly. Yes, Abhi, you're correct. You can do power I also as the power function called with base and I. It's just that this thing is slightly slower. This thing is order log I for a single one. So total it will be order n log n. So it's slightly slower, but you can do it. It's negligible for most purposes. But just know that this is the faster method. This is order n. Now you calculate the inverse powers. So notice in your formula you had this p upon I in the denominator, which becomes like this, right? How do you do this? You use Euler's theorem, Euler's-Torsion theorem or Fermat's little theorem, which basically says, so we have the statement here, 1 upon base in the mod becomes equal to this thing. Just treat it as a fact for now. I won't go through the proof of it. It's again a number theory topic which we don't want to cover. Just treat that this is equivalent to this when the mod is prime. This is important. Now that's the reason why we picked 10 to the 9 plus 7. Basically it had to be a prime because this thing only holds for primes. This statement only holds for primes. It doesn't hold for non-primes. For non-primes there are other methods to get this value, but they're more complex. This is the easiest, like the RHS is the easiest value. Notice this is mod minus 2 in the exponent. You can read up on Euler's theorem or Fermat's theorem if you want to know the proof of why this is correct. But the idea is 1 upon base under the modulo can be written as this thing. It's the same. Under the modulo. Don't think of it like a fraction anymore. Like intuitively, don't think of it like 1 upon 30 as a fraction. Think of it like 30 inverse. Basically, 30 inverse is some number x in the range 0 to 30 such that 30 times x is equal to 1. That's how you should think about inverses in modulo range. You don't think about 1 upon 30 as some quantity. That doesn't make sense under modulo range. Right? So you think about it like this. That it is the 30 inverse is some number x in the modulo range, in like between 0 and the mod. Sorry, this is a typo, bad typo. Yeah, in the range 0 to mod minus 1, such that the product of these two elements is 1. Notice what 1 upon 30 gives you. 1 upon 30 is also the same thing, right? It's in the normal integer domain, it's a number x such that when multiplied with 30, it gives you 1. That's why x is 1 upon 30. In the modulo domain, the definition is same. Yeah, it's known as inverse modulo. Yeah. So you calculate the inverse modulo, the inverse power. So this is basically 1 upon 30 calculated in power inverse variable. Sorry. And this is base to the power mod minus 2 mod. How much time does this calculation take? Log of mod, which is also pretty fast because mod is just 29 plus 7, so log is just small value. It's log n roughly, right? Now let's look at the other portion of this pre-calculation. You have these 3 lines. So inverse of 0 is 1. Why? 1 upon 30 to the power 0. This thing is 1 upon 1, which is just 1. So that's why 30 to the power negative 0 is just 30 to the power 0, which is just 1. That's the reason why inverse 0 is just 1. Now what about the other ones? This statement basically says, where should I write this? Here. 30 to the power minus I is equal to 30 to the power minus I minus 1 times 30 to the power minus 1 whole under modulo. This is basically what the statement says. Can you use some light color, please? Or instead of, I mean the marker itself, right? I'm not sure what happens if I use a lighter color. I mean, is it right now less bright? You won't. I mean, I can use yellow if you guys want. Yeah. So this expression is basically, take the example 30 to the power minus 7 is equal to 30 to the power minus 6 times 30 to the power minus 1. That's what you're doing in each operation. You're taking the just smaller power and multiplying it with minus 1 and getting it. So that's what this operation is. And you have this precalc function, which basically just gives you powers of 30 and inverse powers of 30. Now you have build function. Now we come to the hashing part, actually, the hash array, which we were talking about. H array, H function. So hash array is basically hash of I is trying to denote H of Pi. That is the hash of the first I elements, the prefix, the first I elements. You can think of it as this way also if you want to. S12I, the hash of the first I elements. That's what hash I denotes. So what you do is you take the length, you loop from 0 to n, because we said that we can keep on concatenating characters at the end, one after the other. That's why it was rolling, right? You say if this is 0, okay, this is some syntax errors. I'll fix it up and re-upload it on Discord and everything. Yeah, I'll show you where is the exact used. It's used here. So if I is 0, then you put 0. Otherwise you put hash I minus 1. Okay. And you have this expression also. So what you're doing here is, I'll just explain it in like how mathematically it looks. It looks like this. H of S12I is equal to H of S12I minus 1, which we know, times plus, because there is this add, I should use red only. Red works well on both the displays. Oh, asked Wilson, ignoring power of Sidhant 100. I mean, I don't know what your question was. If your question was, okay, pupils specialist kaise बनते हैं, I don't know that. It's not related to the topic. So yes, we had this. So H of Si is equal to the previous term's hash value plus you basically take si. When you do this minus a plus 1, you're basically taking the actual digit, like actual value. So if it's letter a, then this becomes 1. If it's letter z, then this becomes 26. It's just the ordinal value of that letter. And when you get that letter, you say letter into 30 to the power I. This entire thing mod. That's what you're trying to calculate, right? We already derived this formula previously in one of the previous slides, that this formula is correct. I just wrote this formula in programming terms here. I used hash I for this. I used hash I minus 1 for this. For this entire expression, I use this thing. If we have a, then it becomes negative. Correct. So if you're using, I'm just assuming that we have small letters a to z in this example. If you have capital letters, then use capital A here. If you have small letters and capital letters, then use a function here. Call a function f of si, and that function should control what to output. Like if it's small a, it outputs 1. If it's z, it outputs 26. If it's capital A, it outputs 27. If it's capital Z, it outputs 52. So on. Like just control it using some function. Okay, so you calculate the hash value. This is it, and this is this condition that if you're going from the 0th element to the 0th element, then you don't have anything in previous. Like that's the first element. So then in that case, just add 0. Don't add anything here. Just add 0. That's the ternary operator. Use of ternary operator. We'll see. Like I think it's like it's in the latter part of the lecture. I think like 15 minutes or 20 minutes more, and then we'll see the applications. It's mainly string data structure, string questions. Yeah. So what about get hash function? We discussed that we want to be able to calculate this hash fast, right? This is also the formula we already derived here. This is the formula, right? We just write this formula in programming terms. So we write hash y minus hash. So if you are trying to calculate the hash from x to y, in this formula, it basically means h of y minus h of x minus 1 whole multiplied by p to the minus x under the modulo. That's it. So here it means the same thing. You take hash of y, you subtract hash of x minus 1, and if x is 0, then x minus 1 is just negative, so don't subtract anything. The idea is this: if this is y, this is x, you take the entire thing's sum and then you subtract out this portion from it. So you're left with only the blue portion. This portion is the only thing that you're left with. This is x, this is y. And so when you're subtracting out this portion, you actually subtract out up till x minus 1. And if x is 0, you can't subtract anything because this is negative index. So then you just subtract 0. Otherwise you subtract this much. Notice we used a negative sign here. That's why we had everything had a reason. Like we weren't adding stuff just because we want to. We had this condition on res less than 0 because of that thing. And here also it should have been res less than 0 because we sometimes have negative values added or subtracted. It's not always positive values being added. So once you do this, now notice in your formula you also had this, right? The multiplication with base to the power minus I. Now you do that. So once you calculate the res, now you multiply it with inverse to the power x minus 1. Yeah, I think there's a typo here. This should be inverse to the power x. Yeah, sorry for the typos. I mean, there are 2 or 3 typos here, but it just should be inverse to the power x. I'll fix the code later on once this lecture ends. But yeah, but like even if you find someone else's library, more or less everyone writes it similar way. That's the idea. So in order 1, we are able to calculate the hash of x to y. Why is it order 1? Because add function is order 1, mult function is order 1, and we are just using hard-coded values. We already stored the powers and the inverse powers. The precalc function was that's why so useful. You already have this power and inverse power, these two arrays pre-calculated. So now everything just works out fine. You don't have to calculate them on the go again and again. So that's why this method is O1, this build is order n, and this pre-calc is also almost order n. So everything is fast. Just think about, like, for each prefix, you map it to an integer. Like, that's the easiest way to think about it, Aditya. Each prefix of the string, you map it to an integer. And now, for any substring, you can get an integer using this math method. Each prefix is hashed to an integer. And don't think about the tiny details of how you calculate this subarray hash. Just know that you can, when you're thinking about it from a abstracted level, that I can do this. I can calculate the hash of any subarray now, using just calling this method, and this method will give that to me in O1. Yeah, so now what everyone was waiting for, I think, analysis. A lot of people were interested in this. So fix the values first. Your P should be greater than the alphabet size, as explained earlier. Reason being, yeah, pre-calc is not directly used, it's just to create the arrays, correct? It's just to create the power and the inverse array, so that you have all the values done, so that these methods can be fast. Your get hash specifically should be fast, because you will call it a lot. You will, in a lot of like in a lot of applications, you will call this get hash method a lot. So this should be fast. Like, you don't want even a log-in factor. I would say you want order one. Okay. So firstly, why did we pick the base to be greater than the alphabet? Well, the reason was simple. If you pick the base to be less than the alphabet, let's say you pick base to be 2. So you're doing a into 2 to the power 0 plus b into 2 to the power 1 plus c into 2 to the power 2 and so on. You'll have confusing aspects when the value itself is also 2. When b is 2 itself, you'll have confusion. Yes, the precalc function is okay. Yeah, I didn't specify this. These functions are just for there. I don't have a main function for this code, but the idea is this, correct? That precalc function is just called once in the code at the start. Yeah, so precalc is just called once at the start, right? And build is also only called once. You even don't call build multiple times. I mean, if you have multiple strings that you want to hash, then it's a different thing. But if you only want to hash one string, then you call build also only once. The only thing that's called multiple times is get hash. That's why get hash has to be fast. It gives you the hash of any substring. So you can get a hash of any prefix, you can get a hash of any suffix, you can get a hash of any substring. So normal, like Si to J. So we need the base to be greater than the number of alphabets, because otherwise there's a confusion here. That if b is 2 and base is also 2, then you like get confused. What's happening? And you have more collisions. Your mod should be a prime. We explained earlier only that there is a mod inverse thing that we want. So that's why it's a prime, right? Because you want to be able to calculate this thing. And Euler formula only works, Euler's theorem, whatever, only works if the mod is prime, which we used here. I'm just copy pasting the screenshot. Okay, now my college is NUS, National University of Singapore. Why high probability? So earlier we said that hashing gives us high probability of correctness. Given two random strings A and B, what is the probability that they will map to the same thing and they are unequal? Yeah, Ayush, I'm not Aryan, I'm not sure what the exact name of the theorem is. I might have misremembered it, but doesn't matter really. So if you're given two random strings A and B such that A is not equal to B, what is the probability that this is equal? Meaning they collide, which is bad. This is a bad event. You don't want this to happen. But what's the probability? We just explained earlier that it can't be 0 because of this argument that you have a left domain and a right domain, and the size of the right domain is smaller than the size of the left domain. So it can't be 0. There must be some probability. That's the poll question. Okay, I'll just say, so what you do is you just call the precalc function first time, Aditya, and then call the build function on the string that you want to hash. That's it. Afterwards, anytime you want hash of any substring, you just call get hash method. You won't call these methods explicitly. These methods inside them will call the add and the mult and everything. So this is the, and the function number, you don't call them explicitly. Yep, so what's the probability that the hash of the two things is the same accidentally? Is it 0? Is it 1 upon square root mod? Is it 1 upon mod? Is it 1 upon mod square? Yeah, so I think like roughly 50% of the people got it. Correct. Yeah, the majority answer is correct. It is 1 upon mod. I'll explain the reason. The reason is, okay, let's say you pick the string A first. Let's say you pick the string A, arbitrary string. Let's say I pick the string A as apple, random string. Okay, apple was here somewhere. It got mapped to an integer using the hash function. Let's say it got mapped to 7, value 7. After the modulo and everything happened, it came out to the small value. Now you have another string B. It gets mapped to something here, right? It can get mapped to anything here. If you're picking this B randomly, it can get mapped to 0, it can get mapped to 1, it can get mapped to mod minus 1, anything. That's the range of this output, right? Because it's within the modulo. What's the probability that it maps to exactly the value 7? Out of all these possibilities, it has these many possibilities, but it gets mapped to exactly 7. What's the probability of that event happening? So basically think of it like these are different bins. This is bin 1, this is bin 2, this is the last bin, and you're throwing a ball. The ball is this string B. What's the probability that this ball lies in the, like, goes in the 7th bin? That's probability is 1 upon mod, because all the bins are equally likely, we are saying, and the probability that it goes into one of them into a specific one is 1 upon mod. And this time I was fixing A. Now you can fix another A also if you want to. You can fix some other A like orange, and maybe it gets mapped to 10, and then talk about B again. And then B, what's the probability that B got mapped to 10? That's also 1 upon mod. So that's why the answer is 1 upon mod. Hope everyone's clear with that. It's just not this much, it amplifies. So you have to be very careful when you're using hashing. You have to understand the basic probabilistic arguments clearly so that you don't get wrong answers. So what I just now showed is, if you take any two strings A and B, where they are not equal obviously, and you hash them, probability of them accidentally giving hash of A equal hash of B, probability of them giving accidentally giving hash of equal hash of B is 1 upon mod. Which portion to repeat? That why is it 1 upon mod? I just said like apple is one element, it gets mapped to 7 for example, B is another element, another string, and it can get mapped to any of these elements, 0, 1 or 2 or up to mod minus 1. So out of these, all these elements, what's the probability that it will map to 7? The probability of that event happening is 1 upon mod, because you have mod choices here. So the denominator is total number of outcomes. Favorable outcome is just 1, which is get 7. So that's the 1 upon mod. That's how you get. Okay. Now, so we showed that getting a false positive. What I mean by false positive is that you thought they are equal, but they are not equal. That's what false positive generally means. That you thought that the two strings, because they hash to the same thing, like let's say apple and orange both hash to the same thing, so you thought that these original strings must have been equal, but they are not equal. So that's a false positive, that you got a positive on a thing, but it's actually not true. So the probability of getting a false positive is 1 upon mod. If we do k such comparisons in our algorithm, then on average, k upon mod will give us false positive. What I mean to say is, let's say you have x1, x2, xn. You hash all of them. Okay. Now you say I compare h of x1 with h of x2. I compare h of x1 with h of x3, and so on. I compare h of x1 with h of xk. Let's say you only had k elements. So you had k strings, you hashed all of them. Now you compared all of these things. Number of comparisons you did is order k. Right? In each comparison, there was some probability that you failed, that you thought that they're equal, but they were not equal. Because the hash came out to be the same, this thing came out to be the same, but actually x1 is not equal to x2. There is some probability of that event happening, right? The probability is 1 upon mod. So on average, how many times would that have happened? Let me give you an example. Let's say this is a coin flip, okay? That this thing comes out to be equal, given we know x1 is not equal to x2, okay? Let's say probability that they come out to be equal is 10%, okay? So let's say it's 10% probability of hx1 to be equal to hx2, or xi in general, and you have 70 elements. So you're comparing hx1 with hx2, and so on, hx1 with hx71. Okay, you're comparing 70 such elements. How many times will you get collision on average? Your probability of collision is 10%, and you have 70 such elements. How many collisions will you get? Roughly, on average. The argument is on average. So options are 0, 7, 14, 35. Obviously you can't get all the collisions, right? Because the probability of that event happening is only 10%. Like, it's very unlikely. It's possible, but it's very unlikely. What's the most likely event? Correct. So most of people got it. It's 7. I won't cover why it's 7. It's like a probability argument. It's fairly elementary if you have taken a university level math course, or even 11th, 12th high school university math courses. So these many comparisons failed, basically, k upon mod, because the probability of each one was 1 upon mod, and I just gave you the intuition that if you do k such comparisons, then the probability becomes k upon mod. That's why I gave you this 10% 70 example, just to show you that it's the same thing. You're multiplying. Now, why is this bad? Why is this amplification of error bad? Where does it where is it bad for us? Let's take this example question. Okay, in this example question, your mod is 10 to the power 97. You hashed a string s of length 10 to the power 6 and took all the 100 length substrings of s in a set. So what the question asks you is, let's say I give you this question: given a string s, the number of distinct substrings of length 100. So you have the string s, right? And you take the first 100 characters, then the second 100 characters, then the third 100 characters, and so on. And for each of them, you calculate the hash value. Let's say the first hash value of 1 to 100 came out to be 30. The next one from 2 to 101 came out to be 35, and so on. And you put all these things in a set. I'm talking about a C++ set or a mathematical set. And the number of entries that you get in this set is basically the number of different substrings you have of length 100. That could be one algorithm to solve this problem. Do people agree with this algorithm itself? That's a valid algorithm. That's a attempt of an algorithm. Now we'll show it's bad. Hashing will actually fail here. So our algorithm works under the assumption that if two strings are different, they should hash to two different things. If that doesn't happen, then we get some error. Let's say there was this string in between of 100 length x1 and there was a string x2. Actually x1 and x2 were different, but they both mapped to the same thing accidentally by luck. We already noted that the probability of this happening is 1 upon mod, which is like 10 to the power minus 9. And how many such comparisons are important to us for this question? And choose 2, or more like this many choose 2, which is roughly 10 to the power 12. Why? Because how many strings do you have of 100 length? 10 to the power 6 minus 100, right? These many strings you have. Yeah, I'll just Arjun, the next slide is about the fix, how you fix it. I just want you to understand what's the flaw in the argument here, so that you can tweak it according to yourself for different questions. So you had these many 100 length strings, and every pair you have to consider for a valid comparison, and you have such 10 to the power 12 such pairs, and the probability that a pair failed is 10 to the power minus 9, 1 upon mod, which is like 1 upon this thing, which is roughly 10 to the power minus 9. Just ignore the plus 7, it's negligible. So how many failed comparisons would you have had in total? You had 10 to the power 12 total comparisons, and the probability of each comparison failing is 10 to the power minus 9. So in expectation, almost 1000 comparisons failed. That means almost 1000 times you accidentally thought that two different strings are the same string, because the hash came out to be the same. Almost 1000 times you accidentally thought that this is the case. Okay. Now even if instead of 1000 this was say 20, then also it's a bad algorithm. Even if it's greater than 1, it's a bad algorithm. Ideally it should be something like, in expectation, the probability of this event happening is 10 to the power minus 3 or minus something. If it's greater than 0, it's a bad algorithm. This thing shouldn't be greater than 0. It should be much less than 0, 10 to the power minus 1 or 10 to the power minus 2. So here you can get a wrong answer on your algorithm, because you mapped two different strings x1 and x2 to the same hash. So in your set only one element is there, but actually there should have been two elements. So what's the fix? Use multiple mods. In my case, I'll just explain with two mods. If you have mod 1 to be 10 to the power 9 plus 7, mod 2 to be 10 to the power 9 plus 9, and change your definition of hash function to be this, which is, if I'm hashing, let's say, the variable apple, the string apple, I'll take it as a pair, C++ pair. The first element will be the hash of apple using 10 to the power 9 plus 7. The second one will be hash of apple using 10 to the power 9 plus 9. How does this help us? Think about what's the probability of pairs colliding with one another. Earlier we were saying, what's the probability of hash 1 of apple colliding with hash 1 of orange? That was 1 upon mod. Now probability, the first pair, this thing collides and this thing collides, both the thing match, is 1 upon mod 1 times 1 upon mod 2, and I picked both of them to be reasonably big. That's why it's roughly 1 upon mod square. Both of them are almost the same, so it's roughly 10 to the power minus 18. That's why we have this. And now think about how many false positives you'll get. So the number of comparisons you did was almost 10 to the power 12, right? Here we said it's 10 to the power 12. So 10 to the power 12 multiplied with this 10 to the power minus 18. So in expectation, you'll have 10 to the power minus 6 failed comparisons, which is not even like, thinking about this quantity is very hard. Just have an idea. If this quantity was, let's say, 10 to the power minus, let's say this quantity was 1 upon 5. Then it means with probability 1 upon 5, then it means almost 0.2 of your comparisons failed. 1 upon 5 is same as 0.2, so let's just write it as 0.2. If this value was 1 upon 5, what it meant in English was almost 0.2 of your comparisons failed, which could have meant that maybe in one run when you submit your code, maybe 2 comparisons failed, maybe 7 comparisons failed, maybe 0 comparisons failed. But when you have such a drastically low value of this order, 10 to the power minus, basically anything like less than maybe 10 to the power minus 2 or something, anything less than that, then it's kind of saying that when you submit, in expectation, these many errors are going to happen, which is very low. So most of the times it's just going to be 0, like no false positives came out, 0 false positives came out. So that's the modulo trick which a lot of people use, using multiple modulos. I just used 2 modulos in this example. You can even use a triplet or a 4 element thing. Just pick different primes and do it, and the probability will like decrease 1 upon mod to the number of mods you're picking. Let's say you're picking m mods, then probability will be roughly this much. Generally speaking, for practical purposes, you generally just need 2 mods in most cases. You generally don't need 3 mods or something, but you can if you want to. So this is the thing. Now what are the 1e9 plus 9 is also prime? I think it is, not sure. You're correct. I think it is. I don't remember it offhand, but yeah, they should be prime because of the inverse modulo thing. Yes, the mods need to be different, otherwise it's not helping you. Otherwise it's just like writing this element again, right? If your hash of a certain string came out to be 30, then now you are just writing pairs of 30, 30, which is useless, because if the first element is 30, then the second element will also be 30, so it doesn't help you. If they're different, then it can be like, now it shows 30, 70 for one, for let's say apple, and for orange it shows 30, 60. Then it's helpful for you, because even though you had a collision on the first pair, on the first modulo, but you didn't collide on the second modulo, so that's good, because in total this pair is not equal to this pair, so that means the hash were different. What if the mods are same but p is different? Then also it will work. Generally people keep mods different. If you keep the base different, then also it will work. The analysis of the maths might be different, but the high level idea that it will have lesser collisions will still work. Could we use a larger single primes rather than using 2 primes? Yes, you can use a long prime, like 10 to the power 18ish prime. The issue that you'll encounter is, so notice you had a mult function, right? Now in the mult function, if you get 2 numbers of the order 10 to the power 10 to the power 17, you get a as 10 to the power 17, b as 10 to the power 17, you need to be able to modulo them with 10 to the power 18ish prime. You need to be able to multiply them first. How will you multiply them? If you multiply them, you'll exceed long also. So either you need int 128, or there's this Russian peasant multiplication thing, you can Google it up, Russian multiplication. You need one of the 2 things to handle the multiplication when it's overflowing. So that's why people use 1e9 plus 7 as their mod instead of 10 to the power 18, because when you multiply, you don't want to overflow. No, Sayantan, that's a good question. You don't have to check. So that's the thing. You just hope on faith that it is different. And basically our probability analysis showed us that with a very high probability, like with almost negligible probability, 10 to the power minus 6 is almost negligible probability, they are going to be different strings. They are going to be apple and orange actually mapping to the same hash. So we don't care. We say that 10 to the power minus 6 probability event happening is so unlikely that we'll risk our submission on that. That's how like randomized algorithm submissions work when you submit a randomized algorithm code. Even if you apply mod to each operand before multiplication, your mod is still of the order 10 to the power 18 if you're thinking about that big mod. So a is 10 to the power 17, then even after applying the mod, it will still remain 10 to the power 17. You need to be able to calculate the value mod square in your integer long int 128 something. You need to be able to calculate this value. If you can't calculate this value, then your a into b won't work. do people make submission hacks and how to avoid? Good question. I have this last slide on pitfalls which basically discusses this, and there are further readings which are on like anti-hash test cases or how they are designed and how you can overcome them. Hashing is a proper valid technique. It's not like some scam solution. It's just that you have to understand the probability argument basically somewhat, and you need to be smart about randomizing some things. Anyways, let's move on to the applications so that people just understand why we are doing all this stuff. So given a string S, find the largest substring which occurs at least twice in the string. So the naive way to do this would be, I'm not sure, KMP maybe. I think KMP can do this. The trivial way would be that you just pick a substring Si to j and then run another loop on the string to check whether you can find another occurrence of this. This thing is very slow. It's order n cube, the one that I explained just now, because number of pairs like this are n square, and for each pair I'll start from every vertex, start from every start point to compare, which is another n, and from that start point my comparison will also take another n, so it's n to the power 4 actually. It's pretty horrible. In using hashing you can do it in roughly order n. So n log n. What you do is you change the problem to say, is there a substring of length k that occurs twice? You say this problem. Now notice on this problem's answer is yes or no. If the answer is yes, you know a string of length k exists, so you can binary search on the upper part. If your answer is between 0 to n, 1 to n, you pick your k to be mid by 2, n by 2. You check whether the answer is yes or no. If the answer is yes, that means there exists a string of length k. So you know your answer must lie in this portion. So you now pick k to be 3n by 4. Let's say the answer is no. So you know the answer lies in this range, and you keep on doing this. So if you can answer this question fast, the question that I explained just now, this yes or no question fast, then you can solve the entire question. Because if you can do this in order n, then using that binary search that I just explained, you can do the entire thing in n log n. You're binary searching over the domain of size n. It's not subsequence. I'm saying substring. I'm not saying subsequence. There's a difference. So how do you do this in order n? It's just as we explained. If you fix a k, what I just said earlier, take every k length substring and hash it and put it in a set. So you take this k length substring, this k length substring, this k length substring, and keep on putting them in a set. Okay, actually this will take n log n. My bad, because I'm putting them in a set. Right? So take each k length substring. For fixing k, we will require loop, right? No, I'm binary searching on k. I say pick value of k to be 20. If the answer is yes, that means there exists a 20 length string. Then there will exist a 25 length string also. Why is that true? What I'm saying? Think about this string. If the answer is, let's say, this string here matching with this string here, and the length of these strings is 30, then any prefix of these two strings also matches, right? So there is a 29 length string also, there is a 28 length string also, and so on. There is a 1 length string also. That's why you can binary search, because all these values will also give you yes, because there are prefixes here which are occurring twice. So everyone understands this? Does everyone get that binary searching works on this problem, this decision problem? And then once we have said that it's binary searching, So now we have to solve this problem fast in order n log n or something. For a fixed k, I fix the k. Let's say I fix the k to be 20. Then I say pick every substring of length 20 and hash it. So I basically hash s1 to 20, I hash s2 to 21, I hash s3 to 22. I take all these hashes, put them in a set, and then if the size of the set is the same as the number of elements here, then that means nothing collided, or basically no two strings were the same. And if it's smaller, that means there were strings that were same. Basically each of this is now an integer. Let's say this is x1, this is x2, and so on, right? All of the hashes are now integers. If any two numbers here are same, let's say x3 and x1 and x5 are same, if two numbers are same, that means their original string was also same. So I found one. But if they are not same, if all of them are unique, then there is no string of length 20 which occurs twice. So I just get all these x's, then I can either put them in a set, or I can put them in a vector, sort the vector and check for uniqueness or whatever. The idea is I have to check whether all these elements are unique or not. If they are unique, that means twice, because otherwise its hash should have occurred twice. But if there is a value which is repeating, that means there is one. Do people get this? Yeah, n minus k should be the size of the set. If it's not, then yeah. Cool. So we have another application here. So you can do hashes for strings. You can even do hashes for the reverse of a string. So given a string s and q queries of the form li, tell if this substring from li to ri is a palindrome or not. So you're given the string, let's say li is here, ri is here. You have to tell whether this substring is a palindrome or not. That is, it reads the same from forward to backward as from backward to forward. It reads the same. So what's the idea here? The idea is take your string s, hash it, take the reverse of your string s, hash that also. Okay. Now in the normal strings hash, you can get this subhash from L to R in this order, left to right order. So let's say this was cat. Then you get c into 30 to the power 0 plus a into 30 to the power 1 plus t into 30 square. Just think about it like that. Now in the reverse string, it will look like tat, right? You hash this also. This looks like t into 30 square plus a into 30 to the power 1 plus c into 30 to the power 0. And these things will mismatch when you hash them with high probability. Obviously, whenever I say they'll mismatch or they'll match, I'm generally saying with high probability, so I'm ignoring that term. When will they match? If this was a palindrome, if this was CAC, then the reverse would also be the same, and in the reverse string, the hash would have come out to be the same. So do people understand what we are trying to do? We hash the normal string, get this subhash from li to ri, we take the reverse string, also hash it, and in the reverse string also take the subhash from li to ri. Obviously the indices will change slightly. Sarthak, for even length and odd length is the same, because this property of left to right being the same as right to left doesn't depend on odd even parity for palindromes, so you don't care. So maybe in the original string, this was L was 3, R was 8, and the original string was of 20 length. In the reverse string, now here this was S0, S3, S8, S20, S1. In the reverse string looks like S20, S8, S3, S1. So you're actually querying this point and this point. Your query points change in the reverse string. That's an implementation detail that you have to keep track of. Here your L and R are 3 and 8. Here your L is probably 12 and your R is 15. No, 17. Yeah, you have to just keep like this L and R get changed to this ones. You have to just keep track. This is a arithmetic thing. 20 minus 8 is 12 and 20 minus 3 is 17. That's how I did it. That's where the positions will be in the reverse string. Right? That's how the reverse string will look like. S20 followed by dot dot, S8 followed by S3 followed by S1. So we are calculating the hash of this thing. If the hash of this thing is the same as the hash of this thing, then they are a palindrome, because S3 to S8 looks the same as S8 to S3. Do people get this? And why is it O1 or something? Like, I can answer each query pretty fast. Each query I can answer in O1. But if we need plane of length 3, I don't get your example. Arak, get in trouble. If we need a palindrome of length 3, I just took an example of length 3, right? Cat, tack. Okay, your example is length 3, right? Like whatever. Your example is this. So if you reverse it, think what will happen to the string. It will look the same, right? And that's what we are trying to exploit here. That upon reversal, the string looks the same. Hope it's clear to everyone. If you have any doubts regarding this palindrome question, just ping. Okay. Now, an updated version of this question, but in this forward we check RAC and reverse. We also get RAC. This forward we check RAC and reverse. We also get RAC, but not on the same index. Correct. It was not on the same index. That's why I said to you that if it's 3 to 8, you have to query in the reverse RAC on the correct indexes, which is 12 to 17. You have to keep track of the indexes. But that's just a simple calculation. This L is basically 20 minus this L. Sorry. This L is basically 20 minus this R, and this R is basically 20 minus that L. That's like a 2-line thing. The positions will change, you're correct. Okay. What if we have character updates also? Can anyone think what we can do? I won't explain this in detail, but what if the person can update a character? He can say change S of X to Y. So he'll give you in an update X comma Y, and he'll say X character should be changed to the Yth letter. He has these operations also. So he can change the characters of the string at some times if he wants to. Yeah, so you can use segmenting. So the power of hashing comes with, like, when it's because they are now integers, you're thinking about integers, you can do this sort of combinations of hashes and thing. Basically, I'm just giving you the high level idea of how the segmentary thing will look like. In a segmentary, if you have a node which is representing the chunk from node 1 to node 4, character 1 to character 4, and the chunk which is representing from character 5 to character 8. Let's say this hash is to A, that is hash of S1 to S4 is A, and hash of S5 to S8 is B. Then you can calculate the parent hash. How? A into 30 to the power 4 plus B whole mod. This is hash of S1 to the power 8, S1 to 8. That's the hash value. This is your combine basically. In a segmentary you have a combine, right? That you take two small values and combine it to a big value. This will be your combine now. If you have a node from 1 to 4 and a node from 5 to 8, your combine will look like this. Oh yeah, sorry. Yeah, my bad. It's actually the other way around. A plus B into 30 to the power 4. Correct. Thanks for pointing out. And Balgopal Patro. It's actually look like this. You can think about why it will look like this. That's the idea. So segmentaries work. So you can just keep on going down the segmentary and update the leaf and then when you're coming back up, just update every hash value along the way on the combine. Now also you can do range queries on the segment tree, that what's the hash value from si to j. You can think about how it will work, but just have this idea that in principle we can do this combine. So you can do queries also, and everything works out. You just get a additional log factor because you're working on segment trees. So you can have these kind of things here, like you can have you can put hashes in segment trees and combine them. That's what I wanted to tell with this. And notice this, yeah. So there's this another question. Given a string s, find the length of the longest palindromic substring. This is a very generic question. People do it using DP and everything. A lot of times I've seen a lot of people do it using dynamic programming and other solutions. I'm sure you guys know of like n square dynamic solutions, dynamic programming solutions. Yeah, this is the n log n approach. So given a string s, you have to find the longest palindromic substring. So firstly, again, you can binary search on the answer. If you know for a fact that there is a palindrome in the string s of length k, then there is a palindrome of length k minus 2 also. Just remove the first and the last character. Think about this much. That's also a palindrome. And just think about this much. That's also a palindrome. So if there is a palindrome of length k, then there is a palindrome of length k minus 2, k minus 4, so on. Note, I'm not saying about k minus 1 or anything. The parity matters. In this case, the parity matters. Because to go from a palindrome of length k to a smaller palindrome, I have to remove two characters. One from the left, one from the right. So I can assure you that there is a palindrome of length k minus 2. I cannot guarantee you that there is a palindrome of length k minus 1. Maybe there is, maybe there isn't. And similarly, k minus 2 assures that there is a palindrome of length k minus 4 and so on. So the function is binary searchable, because if I have this yes, that there is a palindrome of this length, then all the other odd or even elements are also yes, and I know k plus 2 is no, and everything to the other end is also no, because k was the largest palindrome that I found. That's the assumption. So how does the question reduce to our problem? So we basically say the question is now, is there a palindrome of length k in S? Yes or no? So if we can answer this question fast, then let's say we fixed k to be 30. We got yes. Now we know in the even numbers from 30 to n, let's pick the next one to be somewhere here. Even numbers only. And keep on doing this binary search. But if the answer is no, then we know that we can't make 30, so we can't make 32, 34 or anything else. And that's why we need to look down. That's the idea of binary search. You have to do the entire algorithm has to be run twice because of odd and even. Once you run it for even case, once you run it for odd case. Because it's binary searchable within the even things and it's binary searchable within the odd things. I can't comment whether how even will affect odd and how odd will affect even. I can't comment. So is there a palindrome of length k? Yes or no? That's the question that you want to answer fast. If you can answer this question in order n or something like that, then you're done. Since we're finding palindrome in 4 and forwards, we can use pairs to store the lengths and store the max lengths. Maybe, I'm not sure what you're trying to say. I think the idea is pretty much same as the previous one. You have a reverse of the string. Okay, do people understand the binary search portion? That why did I say binary search? Like, why does binary search work here? You had a string s and you had a, let's say you have palindrome of length 30 inside it. Then you also have a palindrome of length 28, right? Just remove the first and the last character of the original palindrome. And so on. You have a palindrome of length 26 up to length 2. And similarly, if this was of length 31, then 29, 27, so on. Yes, okay, now I'll explain the sub-problem, yeah. So now how do we solve this question fast? That's the question. So now you do this using hashing again. What you do is you put S as one hash, you do S reverse as another hash, the reverse string. In S, if you fix your pivot to be I, let's say you say I is my pivot. Pivot in a palindrome means the middle character. So let's just, for simplicity, let's just take the odd case right now. So we are taking off odd case. So if my pivot is I and the length here is k by 2 minus 1, the length here is k by 2 minus 1, correct? Sorry, k minus 1 by 2, k minus 1 by 2. Then from I find the hash for the next k minus 1 by 2 elements. I get the hash, so I to I plus k minus 1 by 2 elements, I get the hash. And in the reverse string, I have Sn here, Si here, S1 here. So from I go to R, and here from I go to SL. So from I again pick this k minus 1 by 2 length chunk. I compare them. If they are same, that means across Si, going from Si to SR was the same as going from Si to SL. Both the paths were same. Both the strings were same. That means it's a palindrome. Do you get this? Yes, binary search is only being used to set the value of k. Correct. Binary search is actually not that relevant. I mean, I have to use it because that's how the problem is solved, but it's not really relevant to the hashing principle. Hashing is not involving binary search right now. Like, it doesn't generally. So, but it's required to get the answer. So for a given k, I just showed you how to get the answer. You fix each I, you know k, so you know what is this I plus k minus 1 by 2. You calculate this hash value, let it be A. You calculate this hash value, let it be B. And then you check, are A and B same? If they are same, then yes, it's a palindrome. If they're not same, then no, it's not a palindrome. Again, finding the indices here is like a math problem. You can just get the left and the right point using some arithmetic tricks, which I did similarly here. Yeah, in the previous question we did, right? Yeah, we got the arithmetic things in the previous question. So that remains the same. And that's how you find. And this is the odd case. For even case, you'll say, instead of fixing I, you fix the I and I plus 1. Then you say you're starting from I plus 1 to R here, and you're starting from I to L. So basically you're saying the path from Si plus 1 to SR looks the same as the path from Si to SL. Why? Notice your palindrome looks like how? SL to Si, and then Si plus 1 to SR. This character is same as this character. This character is same as this character, and so on. SL is same as SR. So this path going from Si plus 1 to SR is the same as this part going from Si to SL. Straightforward. So I hope people understand. Instead of the entire reversal, we compare for the two parts around the pivot. Correct. So you you fix the pivot, and for that pivot you say, is it possible or not using this path things. You can do this in order 1. And how many pivots can you have? Order n. So in order n you check each pivot, and for each pivot you check whether it's possible or not. If it's possible for even one pivot, then it's yes. If it's not possible for any pivot, then it's no. Pivot is basically the middle element of a palindrome. So if you have a palindrome ABA, C, ABA, then the pivot is C. For odd length palindrome, it's just the middle element. For even length palindromes, you generally say the middle two elements are the pivot. That is, across this thing, they are the same. When you take the mirror image, like when you flip it. And you're using the reverse string here to basically simulate that flip. So thing to remember here is, even if you can't memorize this algorithm, thing to remember is you have to think about the reverse of the string when you're thinking about palindromes. So at the start, when we input the string, we also have to store its reverse, right? Yeah. So when you just take the string, you just store its reverse also and then do the computation. String reversal will affect computation time. No, it just makes your computation twice slow, right? I mean, instead of doing everything for one string s, now you're doing it for its reverse also. So if it was taking order n time earlier, now it's taking 2 n time. Or if it was taking t time earlier, now it's taking 2 times t. But it's just doubled, that's it, which is pretty cheap. Okay, now I don't think we have time to cover this question. So this is a homework question, let's say. I'll put the solution on Discord later on. You guys can think about it. Also, like, to do with hashing, obviously. So you saw the power, right? Like, I mean, this question, find the longest palindromic substring. This question can be solved by like at least 3 or 4 data structures. It can be solved by palindromic trees. It can be solved by Maneker algorithm. It can be solved by suffix arrays, and it can be solved by string hashing. Palindromic tree, Maneker, suffix array, hashing. But I would say simpler ones like but hashing is much more powerful in the sense palindromic tree is only useful when you have palindromes, or Maneker is only useful when you have palindromes. Both these are palindrome specific data structures. So you, even if you know these data structures, you can only answer, it helps you in tackling questions which are palindrome related. Knowing hashing is very good in the sense that it's very versatile. You can do a lot of things. You can tackle these kind of questions. You could tackle different, like this one, largest substring which occurs at least twice. Now you can't answer these kind of questions with palindromic tree or something. So the way I was trying to explain you the power of string hashing is that you can apply it to a lot of different scenarios where only one of the data structures, string data structures, work. But hashing generally works in a lot of places. So what are the pitfalls? Slow implementation, unnecessary mod operations, using long instead of ints everywhere. I'm not discouraging you to use longs. I'm just saying be aware that it slows down your implementation. So if you get a TLE or something, then you know kind of that, okay, I maybe need to reduce my modulos, or maybe I need to use integers instead of long. You can still use long if you find it comfortable or something. Then there are a lot of off by 1 errors, which even I made while explaining you guys. Off by 1 errors are errors of the form here, that instead of x minus, let me explain. Instead of x minus 1, maybe you do x. Instead of, like, I made this error that this is actually inverse x. So off by 1 errors are very common in hashing because you have these plus minus 1 things and you have to be very precise because it's a numeric value that you get of the hash, and it changes if you just add 1 character more or delete a character. So you have to keep track. Like, this is one of the things that you have to be aware about a lot when you're doing hashing. Can you share link of blog, please? Which blog? This one? Okay, I'll put them in Discord, but they are in the slides and they are hyperlinked. Like, the slides are hyperlinked. So you can just click on this link on the PPT that's on the Discord and you'll get the link. So another thing was, my randomization argument wasn't 100% correct. We were still missing some points here and there. The reason I did that because to make it simpler to understand the hashing technique. How can I extend this class by like, okay, maybe I'll get a pop-up. What happens? So our randomization argument wasn't completely correct. It was a simplified version of the actual thing. And the way you go about it to fix the loopholes, you randomly pick your base as well as mod. So right now you're picking the base as a hard-coded value in our code, 30, 36, something of that sort. Instead, you could pick it randomly during runtime. During runtime, you decide that I'll pick some random number between 30 to 40 as my base. Then the author cannot hack your solution easily because he doesn't know what will happen in which execution. When he executes it once, maybe the value 33 gets taken. He executes it another time, maybe the value 37 gets taken. He doesn't know which value it's going to take. Also, similarly for mod, you can have a list of big primes, like let's say 10 to the power 9 plus 7, 10 to the power 9 plus 9, and maybe 4 or 5 other primes. A lot of things which me and like other people in ICPC do is, in your code book, you write down 10 to 15 big primes. Big primes means primes of the order 10 to the power 9. You just literally write them down, print them out. The idea is you create an array of all these 10-15 primes in your code, just type them out manually, and then during runtime, pick one of them randomly. So if this array is, let's say, of 20 elements, then you just generate a random number between 1 and 20, let's say it's 17. So you say, I'll use the 17th prime. Now, the author can't hack your hashing function easily because he doesn't know in which execution which one will be picked. So you have to randomize your picking of mod and base to avoid hacking classically. So general rule of thumb that I use, or like a lot of people use, is they submit the code once with the normal base 33, 36, 40, some standard typical value, and with the mod set as 10 to the power 9 plus 7, or maybe 10 to the power 9 plus 9, some ordinary value again. So they just pick some mod values and just you submit it, like what I showed you in the implementation, that I had hard-coded constants at places. And if it wrong answers, then I just change my implementation to say, instead of picking the base as a hard-coded value, I'll pick it from some range. And instead of picking the mod as a hard-coded value, I'll pick it from this range. And I just add these 5-7 lines of code to do the randomization part of picking the base and the mod, of fixing the base and the mod. Once the base and the mod are fixed, now the same thing runs pretty much, just with different base and mod. So you randomize the picking from a hard-coded list during runtime. That's the important thing, that during your C++ runtime, you do this. And yeah, you can use a random number. Just the range should be greater than the alphabet. Like you should start from 30 onwards and probably up till only till 100 or something. Otherwise, you'll risk overflowing things and everything. Or like 255 or something. But yeah, you can pick the base at random. Like base doesn't need to have any prime or any special property. Obviously, it's it's likely. Yeah, so code forces especially, I generally put 2 mods in code forces. Generally, if I try to put 2 mods, that is, I put a pair of mods in my implementation. Just a single mod is sometimes risky that it can fail on the sys test. In an ICPC setting where you have full feedback, you can do this. Yeah, you get one wrong answer or something. At most. So that's pretty much it. If you're interested about learning like this anti-hash, how do people create anti-hash test cases, or what's the mathematics behind it, then there is a very good blog on CF. These 2 blogs, they explain anti-hash testing and like the exact probability argument that I didn't go deep into, but this CF blog post that I'm referring to is basically one of these 2, which actually understand the probability argument more clearly, more explicitly. Yeah, and then there are these 3 hashing blog posts which are pretty popular, I would say. One of them is by Lalit Kundu. He is a IIIT alumni, I think. And the other one is CP algorithms. Yeah. The last one is a very good blog by RNG58. You might have known of him. He's a red coder on, I think, CF or something. And he has a good blog on how hashing is applicable to other places. So it's a very interesting topic. You can read about it if you want to later on. How hashing is useful in, you can, instead of hashing strings, right now we were hashing strings, you can hash trees also. So you have a tree and you want to compare whether this tree looks the same as this tree. So notice that these trees are actually the same. I just rearranged the adjacency list, but they are the same. So trees which look the same are known as isomorphic trees. There's just some definition. But to be able to check fast whether 2 trees are same or not, one of the methods is that you hash the tree. That is, take the tree and just boil it down to 1 integer. And if this tree boils down to number 29 and if this tree boils down to number 35, then we just compare these 2 numbers, 29 and 35. If they are not equal, then we say the trees are different. If they are equal, then we say the trees are same. So for this kind of a thing, or let's say you have a set of elements. Let's say the set has 3, 10, 2, 5. This is set 1. And there is another set which has 10, 5, 2, 3. and you want to say, are these both the sets same or not? Technically they are the same because they are sets. Order does not matter in sets. It's 3, 10, 2, 5 or it's 10, 5, 2, 3, you don't care. The order doesn't matter. In that case also, there are hashing functions. You can hash this entire set to some entity, let's say 40, using some hashing function, such that this entity also hashes to 40. For example, XOR all the numbers, but that's a bad hash. Probability wise it will mess you over, but that's the idea, that you can use hashing in a lot of other places. In this blog, RNG58 actually covers those applications. He covers like 1 or 2 applications of that sort, which are not typical string hashing. So but it is hashing nevertheless, and it's great. It has the same maths idea behind it, that there's a probability of failure and you want to reduce it or something. So is string hashing an IOI topic? I would say it's not an explicit IOI topic. I don't think they can actually give you a question in which only string hashing works and nothing else works, but it is acceptable. That means if there is a question and you can find a solution using string hashing, but the author solution is different, then they won't complain about it. I mean, it's possible that there is a string hashing solution also to that question. So knowing string hashing is an advantage, because generally string hashing, a lot of times, like at least in like 30-40% of the questions that you'll see of string hashing, in which you'll end up using string hashing won't be the author solution. It will be an alternate solution, and that's the ability of string hashing, that a lot of places where you don't understand or cannot figure out the actual solution, the author solution, that's the expected solution, you can still figure out the hashing solution because it's relatively simpler. Because you think about it in a brute force manner, that you're comparing strings and your comparison is now fast. Suddenly you can compare any 2 strings pretty fast. So how can you do this question now? Is there any other platform you teach apart from here? Not really, Adi Thakur. I've taken some classes for CodeChef before also, I think 6-7 months back. I think they're present on YouTube. It was DSA learning series. But yeah, that's pretty much it. Use a default code with small tweaks every time. If you apply hash function twice, what do you mean by hash function twice? Okay, if you're saying hash of s, then it doesn't make sense, because this hash of s is an integer now. How are you hashing integers using your hash function? So maybe you need to have another function which takes in an integer and outputs another integer, but I don't think it will have it because of this diagram. When you do hashing h function, now you take this function p. Now if 2 things collided here, then they'll collide later also. If you had string s1, s2 and they collided here, x, so h of s1 was x and h of s2 was also x. Now when you take h of s1 and p of this thing, it will be something y here, which will be the same as this thing. So it doesn't matter. It won't help. Right? So because this is a one-to-one function, so like hashing it again doesn't really help. But yeah, we can find if there is palindrome of size k without the pivot, right? No, you need the pivot. I think you need the pivot. Like you need to iterate over all the pivots. You need to iterate over all the possible candidate pivots. Where can I find the slides? The slides will be uploaded. They have already been uploaded on Discord server. I think someone can share the link here on the chat of the Discord server. Let me just stop sharing my screen. Yeah, so this is the Discord server. I uploaded the slides here, and that's the non-annotated version. I'll try to fix the string hashing code, which I had like 2-3 typos in it. I'll fix it and then and upload the annotated slides with the scribbling that we have done. In case anyone has any doubts, I can stay for like maybe 5 more minutes or something, then we can end the lecture. Yeah. If you have any doubts, if you don't have them, please go ahead. Yeah, you're welcome to it. Amar Shukla, if there is the same hash in the reverse and the original string, then that would mean we have found a palindrome. Correct. So that's what I'm. No. Okay. Good question. Good question. Share screen. Okay. Your prime number should be around 10 to the power 9. Like, it should be around 10 to the power 9. Yeah. I don't think making it smaller generally doesn't help in any way. So making it 10 to the power 6 or something will just be a drawback to you. It won't be beneficial in any way. And making it, I just explained, like, you can't make it like 10 to the power 18 or 10 to the power 12 or something. Why? Because if it's 10 to the power 12, you can have A and B around 10 to the power 11, which you have to multiply. So 10 to the power 11 multiplied with 10 to the power 11 gives you 10 to the power 22, which exceeds long. So that's why 10 to the power 9 is a good value, like roughly around that. That basically squaring that value should still remain within long. That's what you want. If after squaring the mod, because A and B will almost be equal to mod. A will be mod minus 1, B will be mod minus 1, and when you multiply them, you'll almost hit mod square. So mod square should still be within long. If it's not within long, then you don't have a way to store it and do the mod. So yeah, before this, Amar asked a very good question. If there is the same hash in the reverse and the original string, so think about this. Your hashes in the original string were everything of the length k, right? So s1 to k, s2 to k plus 1, and so on. These were all the hashes that you stored. And in the reverse string, you stored sk to 1, sk plus 1 to 2, and so on. Now it's possible that s1 to k hash matches with this hash. That is the first left to right elements. Okay, let me give you an example. A, B, C, D, this is a string, followed by D, C, B, N. No. Let's make this example simpler. A, B, X, Y, B, A. Notice this string doesn't have any palindrome. I mean, one length palindromes only. No 2 length or 3 length palindromes, correct? When you make hashes of length 2, you'll hash AB, you'll hash BX, you'll hash XY, you'll hash BA. When you make hashes on the reverse string, what's the reverse string look like? AB, YX, BA. You'll put in the hash AB, you'll put in the hash BY, you'll put in the hash YX, you'll put in the hash XB, you'll put in the hash BA. Notice AB hash was present in both of them, but still it's not a palindrome. Because here it's present here, and here it's present here. So in the reverse also it's present. This one occurs because of this one. So it's present, but still this thing is not a palindrome. So you need to be careful about this. I hope you get it. But just saying that there is this thing present there doesn't suffice. Can we use same hash functions you mentioned for rolling hash pattern matching? Yes, you can. Yeah. I mean, I'm thinking you're talking about something like KMP, like going from left to right pattern matching. You can use the same thing. I think for string hashing generally, this polynomial rolling hash is the most popular option that people take, in competitive at least. I haven't seen people take other hashing options. It'll take twice the time, but it's possible, right? No, I just showed you an example where if you don't consider pivots, if you don't have the concept of pivots, then you'll just say that the answer is whatever. You'll say, in this case, you'll say that there is a k equal 2 length palindrome, but there is no. You can think about this string and you won't find a 2 length palindrome in this string. But if you just consider these hashes and these hashes as two different sets and think that if they have an intersection, then I have a palindrome, that's wrong. You need the pivot thing. This is a counterexample. String is different, so h of s and h of s is not same. Correct. So the entire string is different. Yeah. I mean, this hash of this string is different from hash of this string, but hash of substrings can still be the same. If there is a AB here and it hashes to 30, then AB here also will hash to 30. they'll hash to the same thing, the AB only. The entire thing, yes, this entire thing might be hashing to say 70, and this entire thing might be hashing to say 60. Different things, because they're different strings. MD5 is not really related to this. So there are, yeah, MD5 is not really related to this. Mainly because hashes like those, MD5 or something, I'm not sure what Murmur hash is. And MD5 I don't think is easy to understand. MD5 is not really helpful for comparative, because you don't get this property that if you know the hash of a certain thing, let's say this is something, string or integer or something, some construct, some structure, and you know its hash value is h. Now you want to add something and know the hash value of the entire thing, that is h of s plus x. Calculating this, you want to do this fast. This is a very important property that rolling hash has, which other hashes don't. Sometimes MD5 I don't think has this. Like, you can't calculate this thing as a function of h of s and x just using these two variables. You can't make this variable in MD5. Yes, Adi, you can compare the entire strings, but that's when you're saying that your objective is to compare two entire strings. Then it's correct. But I was saying you have to compare substrings, right? If you have to compare substrings of the main string, then yeah, then you need the pivot idea. Cool. So with this we end the lecture, I think. Yeah. Alright, thanks for attending. Yeah, welcome.